So, good evening, sir.
Good evening.
So, first of all, easing into the podcast, I would like to ask you, can you please share about your personal journey into astronomy and specifically into solar radio astronomy? That is like a very niche field.
Right. So about my journey into astronomy. So that sort of took place while I was still doing my bachelor's here. So I started to do a bachelor's in physics because I really liked physics, and I somehow managed to convince my parents to allow me to do that, who were pushing me to get into engineering. Yeah. During my second year in physics, actually one of your professors here, Professor Jasjeet Bagla, he's a year senior to me. We both did our bachelor's from the same place. Yeah.
Oh.
So he was in his third year, I was in my second year. He wanted to do a project to measure the speed of light using Reamer's method. Yeah. That was among the first ways to measure the speed of light. At that time, it was not even known if light has a finite speed or not. And that was the idea to do that. We didn't have money. He needed to build a telescope. It was not a one-person job. He was looking for sort of friends and labor here. So we were, I and another person who's now at Indian Institute of Science, Tarundeep Saini. He's a professor there. Yeah. So we got recruited into helping him in building the telescope and doing whatever it would take to do these measurements. And it was amazing experience for me, not just, being in the company of friends, spending the nights at some place watching the skies, but the power of astronomy that, with comparatively simple equipment, with very straightforward ideas, we could measure something as large, a quantity as large as the speed of light, which is really very hard to measure. It seemed like very powerful thing to me. It was also a time when I was reading a lot of Sherlock Holmes. It seemed like I'm playing detective with the universe, right? I have my evidence in terms of the data which I have gathered. I have the realm of what is allowed in terms of the laws of physics. And that's really the only assumption I'm making about the universe, that they are the same everywhere. And just that and the tiny amounts of light which is incident on my telescopes is enough to allow me to answer some pretty profound questions about the universe. So that really helped me decide that, okay, this is what I want to do. The other aspect was that astronomy, which I realized only a bit later, that astrophysics, as we now like to call it, is basically applications of physics to astronomical contexts. They allow you enormous variety of what is it that you want to do. So I could choose to do astronomy and still have a lot of different things to choose from when it came to, diving deeper. The second part of your question was, how did I get into solar physics? So I was a part of the team which was designing the Murchison Wide Field Array. Okay. And that was a project which was at that time a joint project between Australia and the US. I had done earlier my PhD in the field of interplanetary scintillation, which is related to solar physics, but not quite solar. You're studying the heliosphere, but not really the sun. Yeah. So I had a fair sense for solar physics. I realized that this instrument which we are building will be a fantastic machine for solar physics. At that time, it was not one of the science cases which was being proposed. So my director at that time at MIT Haystack Observatory told me that, look, if you think it's a good idea, why don't you build a science case for it? And let's see if we can get the funding for it. So I started to do that. As I started to do that, I needed to learn more about it. And as I learned more, I got even more interested into that. And so that's how I got into solar physics.
Yeah. So your journey and your analogy to Sherlock Holmes, that's quite a poetic start to your journey in astronomy. For the audience here, solar astronomy is a field that has a very small community. And can you explain us some fundamentals of radio astronomy, of how it can be employed in a solar physics context?
Sure. So it's actually very interesting. So the the sun which we see with our eyes, I mean, you all know that the peak of the solar spectrum is in the yellow-green part of the electromagnetic spectrum, right? So, and we are all also taught that stars, their spectra are essentially like black bodies.
Yes.
Right? So the radio part of the spectrum is very, very far away from where the peak of the solar spectrum lies, right? So normally, if I want to study an object, I would want to go to a place where it is brightest, right? Here, you're almost 25 orders of magnitude down in the power which is being emitted, and still it makes sense to study the sun there, because at radio wavelengths, what you're seeing is really not the sun itself, but the corona which is surrounding it. So if you recall the pictures of the sun you have seen taken during total solar eclipses, there is a lot of this fuzzy gas around the sun, which is always there. It has all sorts of structures. Some of them might actually remind you of a bar magnet, and it has, streamers and various other things which you can see. All of them disappear when the eclipse is gone. Right? That's because they're just so much fainter than the sun. Is the same reason as why you can't see the stars during the day. Right? But as it happens at radio wavelengths, it is the emission from this corona which dominates the radio emission which you see. As it happens, this corona is at about 1 million Kelvin or a couple of million Kelvin as compared to the surface of the sun, which is at about 5,800 Kelvin. So it's really amazing in some ways that, something which is completely transparent to optical light now begins to dominate what you are seeing at radio wavelengths. And so if that is what you want to study, you have to go to radio wavelengths. And that is what I do.
So, your ending to this answer brings me to my question. There's this very open problem, coronal heating problem, about why we need to study corona, that it is hotter than the chromosphere and other inner layers of the sun, which should not be the case, very obviously. So what are some leading theories, and how do you think radio astronomy aids to it, like the coronal heating problem?
So that's an excellent question. So as you rightly said, that according to the laws of thermodynamics, right, heat can only flow from a hotter body to a cooler body, and this is really the other way around. So that already tells you that the process which will transport the heat from the photosphere or the chromosphere to the corona will not be a thermodynamic process, right? It will be something else. Now, over the years, we have built enough information about the sun that there is a consensus in the community that the reservoir of energy from where this energy to heat up the corona is being drawn is actually the magnetic field of the sun. Okay. All of this magnetic field is rooted in the photosphere, right? So the visible layer is the photosphere. On top of it sits a very thin chromosphere. And on top of that sits the corona. And the corona and the chromosphere are separated by a very thin transition layer. That's less than 100 kilometers thick. In the photosphere, the most efficient mechanism of transport of heat from beneath the surface, right? The nuclear engine is inside, so that heat is slowly being transported up. It is the convection in the photosphere, which is the primary mechanism for transporting this heat up.
Yes.
The magnetic field which is there is also rooted in the same photosphere. And you have perhaps seen pictures of these supergranules, right? These thermocol-like things which are upwellings and downflows of plasma on the surface of the sun. So as this plasma is being constantly churned, the magnetic field which is residing there is also being pushed and shoved and twisted and turned and so on. So what that is doing is that it is increasing the tension in this magnetic field, right? An analogy of a magnetic field with a rubber band is sort of useful here. So if I keep twisting a rubber band, I'm adding stress in there. And I cannot keep adding that stress indefinitely. At some point, it will break. Similarly, in this situation, I am slowly building stress in these magnetic fields. I cannot keep doing that indefinitely. Under the coronal conditions, when it happens that oppositely directed magnetic field comes close to each other, it tries to relax to a lower energy configuration via a process called magnetic reconnection. So these fields will sort of snap and reconnect to the neighboring oppositely directed field, and all the energy which it will shed will be released as kinetic energy of the plasma which happens to be there. So now I have taken out energy from the magnetic field and deposited it in the corona as kinetic energy. As these things thermalize, it will show up as heat. So this is one of the leading hypotheses for explaining
the heating problem.
Coronal heating. This was proposed by Eugene Parker, the same person after which the Parker Solar Probe is named. And he proposed it as the nanoflare hypothesis. And the idea was that the nano is supposed to signify that it's really tiny, right? It's about a billionth of the size of the large flares which we see on the sun. And the idea is that there's a very large number of them which are always taking place all over the sun. And individually they are too weak to see, but collectively they are dumping enough energy in the corona for the corona to be heated up. Right? So that is one hypothesis. The other leading hypothesis is, it again starts from the same point that I have my magnetic fields which are rooted in the corona, which are being pushed and shoved. And in this process, I set up waves in this magnetic field, right? Waves, as you all know, can carry energy, right? Now, waves in the magnetic fields are called alpha waves. And all I have to now do is get this wave to propagate to a height where I need to heat things up and get it to dissipate there. Once it dissipates there, the energy is going to show up as heat. And this is referred to as wave heating hypothesis. This is the other leading hypothesis. We have observationally the evidence for both of them, but we don't have sufficient evidence
conclusively
neither of them, both of them have certain shortcomings in the sense that the nanoflares have actually been observed, but the distribution of nanoflares on the sun follows the distribution of active regions. And you perhaps already know that the active regions on the sun, they are born at sort of mid-latitudes, about 35, 40 degrees, and then they come closer and closer to the equator as the solar cycle goes on. And they disappear and again start at about 35, 40 latitude. So nanoflares have not been observed at higher latitudes.
At polar regions.
Right, but the corona is hot all over. Yes. Similarly, the alpha waves have been observed, but they seem to be going strong even in the regions where the corona is already hot. So they have not given up their energy, but the corona has already been heated up. And they're turning out to be really hard to dissipate in the coronal medium. And according to current estimates, the amount of energy which they can dissipate is not sufficient to heat up the corona. So perhaps the answer is going to lie that, okay, there is a mix of both of these processes which are,
the heating in the polar regions can be attributed to the waves maybe, and the near the equator regions can.
Right, near the equator, these guys also have a contribution, while the
dominant contribution can be through the nanoflares.
Yeah. So that remains to be settled, but neither of them on their own seem to have sufficient energy being dumped into it at the moment. There's always the possibility that what we are regarding as nanoflares today are not the ones which are responsible for coronal heating. There is another population of much weaker nanoflares, or now you can call them whatever, femtoflares, which are responsible for it, which we are not yet able to detect. That's certainly a possibility.
Yeah, so the very detailed answer has many subtle concepts in it embedded that are, magnetic reconnection. For a student who is coming just out of school, a magnetic reconnection is a very novel process. But for a very involved readers, if we move towards the corona, we talk about things like coronal mass ejections and solar flares. So can you tell us more about, what are these things, solar flares and coronal mass ejections? And, how are they different, and what radio wavelength helps us in studying these phenomena in corona?
Sure. So once again, these flares and coronal mass ejections, all of them are again tied to solar magnetic fields. Yes. So a flare is an impulsive release of energy on the surface of the sun, right? So that energy release is coming exactly because this magnetic field has just too much stress built into it and it must relax. Now, as it relaxes, it's going to heat up the material around it. That is going to show up as, in X-rays and extreme UV wavelengths, and that is what you will see as a flare. Some of these flares also lead to what we call coronal mass ejections, right? CMEs. So there is a chunk of matter which is expelled from the solar atmosphere, which is again a consequence of this relaxation. And so not every flare is associated with a CME, but many flares are associated with coronal mass ejections. The converse is also true, that not all coronal mass ejections have been found to be associated with flares. There are these so-called stealth CMEs for which we have not managed to find any precursors or a signature on the solar disk which has given rise to them. But the vast majority of them are associated with flares. And CMEs are just ejections of magnetized plasma into the heliosphere. Some of them would get directed towards the Earth as well. And their impact is what we refer to as space weather.
Yeah. So if we are talking about space weather, can you tell us more about, why studying the sun is important in the context of our near Earth conditions in satellites and the distance in between our sun and Earth?
Right. So the sun-Earth distance, as you probably know, is about 150 million kilometers, right? It takes, and the typical speed of solar wind is something like 350, 400 kilometers per second. It takes around 3.5-4 days for this plasma to reach us after it has started from the sun. Earth also has a magnetic blanket, right? Earth has a magnetic field. We've all played with compasses. We know that. Yeah. It also acts as a shield against this coronal mass ejections which would come from the sun, right? Like I said, these are a cloud of magnetized plasma, very energetic plasma. If the magnetic field in the cloud is such that it is repelled by the Earth's magnetosphere, it cannot do much damage in the sense that it just compresses the magnetosphere, but it cannot penetrate it and sort of passes by the side. But if the orientation of that magnetic field is such that it is attracted by the Earth's magnetic field, then again this process of magnetic reconnection takes place, and this very energetic plasma can flow along the lines of the Earth's magnetic field now, so towards the poles. Right, you're all familiar with the aurora, right? They are a consequence of these very energetic particles from the sun, which have somehow made their way into the Earth's magnetic field and are therefore being directed towards the poles. So the consequence for us basically comes primarily due to the things which we have in space, right? We have a ton of technology floating around in terms of satellites, which we rely on routinely. Now, those satellites were not designed to be swimming around in a pool of plasma. They're designed to mostly be in a neutral environment. And so so that is one aspect. The other aspect is that the density of the atmosphere itself increases, and that leads to an increased drag on the satellites, which therefore means that their orbits will decay. And so you will have to either spend fuel to raise them again, or they will just fall down sooner. The third aspect is that, the radio communication satellites, which are maybe above the layer where this plasma is now swimming, your radio waves have to traverse through this plasma to get to them. And then on the way back, they have to traverse it again. So these lead to distortions. So for example, your DTH reception might go bad because of this, because they have to traverse this ionosphere a couple of times. Your GPS signals might lose lock. That is why airports cannot rely purely on GPS for landing aircraft, because unpredictably at times GPS simply might not be available or might give you erroneous answers. So they need an independent technology as well to do that. Now we also have constant human presence in space, right? The International Space Station always has a few people living in there. Their exposure to energetic particles grows very high. Even for aircraft. So for example, if you were to fly from here to somewhere in the US, the nominal flight path takes you very close to the North Pole. Those are the places, again, poles are the regions where these energetic particles are converging. So what I read somewhere is that the equivalent dosage which you experience in a flight during such an event is about 100 X-rays here. So to avoid that, then aircrafts have to take longer paths. So that's a cost which then they incur There are other consequences as well because of induced currents, which really affect the electric grids, especially close to the poles. I mean, that's basically Canada and Russia. Those are the places where they feel those impacts. Yeah.
So you talked about radio telecommunications getting affected. So there's this very famous Carrington event in the 1980s, which severely damaged whole Earth's grids almost. So can you tell us if there's any more potential risk given the updated technologies we have now also? Do we have any such potential risks if the sun tries to go wild someday?
So the sun is going to inevitably do that someday, right? It's just a matter of time. It's an extreme event, so it's a rare event, but someday it will happen. I think over time we have only made ourselves more vulnerable to such things because we have a lot more technology which is exposed to these risks. Right? Nothing is going to happen to us sitting on the ground. Right? But that technology is what is going to experience various kinds of outages. And the more is our reliance on these technologies, the more impact we will feel of them. So you will have more satellites on which you might lose control, or something will misbehave, some orbits will decay. Those sorts of things will certainly happen. For the countries at higher latitudes, for example, UK includes impact of a Carrington-class flare in their formal risk registry as among the top 5 things one has to be careful about. And their problems are related largely to the impact of these things on the power grids. What they can lead to is failures of power grids, and the induced current in the grids can actually lead to the transformers being burnt. The problem simply is that those transformers are always built on order, and there is no ready supply that, okay, if my transformer is burnt, I can go and get another one. And if thousands of them are suddenly burnt, there is not enough capacity in the world to replace them quickly. So that is really the reason why it is on their risk register here.
So the risk is always there, somewhat always there.
Yeah.
So zooming out a bit, studying the sun helps us in, studying other stars also that are far away from us, for which we do not have enough information. So can you tell us how is this statement relevant in the radio context, like how studying the sun will help us in the study of other stars?
Sure. So like you said, basically the sun gives us a template, right? Which we can use for understanding what is happening in other stars as well, right? So we talked about earlier about coronal mass ejections. Yes. These mass ejections are also associated with some specific kinds of radio bursts, it's just a name, but they are referred to as type 2 solar radio bursts. Okay, so you can if you see a type 2 solar radio burst, you can be sure that there is something which is driving a shock in the coronal plasma. It is at the shock front that these bursts are born. We have recently had our first observation of a type 2 burst from a different star.
From a different star.
Right, so now it tells us that, okay, something happened on that star, which was probably something like a coronal mass ejection, which was moving fast enough. Right, it has to move at a superalfanic speed in the corona for it to be able to drive that shock, and it would be at that shock front that this type 2 emission would have been generated. So it allows us to, for example, understand things about coronal conditions in that star, because as it happens, the frequency of this type 2 burst allows you to estimate the electron density at the place where it would have been born. So now we can already estimate what kind of electron densities would exist in the corona of that star for us to be able to do that, right? Yeah. So that's an example of how it might help here.
Yeah, so you have advocated for using ground-based telescopes to study sun, but we already have so many observatories at L1 point studying sun. So what is the advantageous front in this context, that why use the ground-based observatories for the sun?
So just like, when we go to a doctor and depending on the ailment, the doctor will prescribe different tests and diagnostics for different things, right? Similarly, for what you want to achieve, you need to gather different diagnostics. So solar physics is inherently multiwavelength. So if I'm looking at, the observatories which you are talking about in space, they are primarily looking at the sun in optical, actually not that much in optical, extreme UV and X-rays. And then they have in situ measurements of the magnetic field and the electrons and the plasma which is swimming by. They can also measure the magnetic field on the surface of the sun via Zeeman effect, right? All of these things tell you about the photosphere, a little bit about the chromosphere, right? These observations are not sensitive to what is happening in the corona. So if you wanted to study what is happening in the coronal regions, that information becomes accessible to you at radio wavelengths. You would also notice that the radio instruments are enormous in size, right? So the Murchison Wide Field Array, which we talked about earlier, now has 256 elements which are distributed over 5 kilometers. The GMRT, the instrument from my home institution, it has 45-meter dishes spread over 25 kilometers. Right? We don't yet have the capacity to deploy instruments like this in space. You might also wonder why would you want to do that even if you had the capacity, because it's much cheaper to build 3 of them so that you can have 24/7 coverage rather than launch one of them into space here. So each of these instruments, they serve a different purpose. They bring in a different piece of the jigsaw which we need to put together to understand the sun as a system, the sun, the corona, the heliosphere, and the Earth as a system.
So that justifies why we need to give some observation time to the star that we live the closest to also. So you have worked with both GMRT and MWA. So what are their unique selling points and how are they different from each other? How do they complement each other, if you would like to say?
Sure. So let me talk about the MWA first. So if you look at a picture of the MWA, it doesn't look like a telescope at all. It looks like, bunch of coat hangers which somebody has distributed on the ground. It has a bow tie shaped antenna. There are 16 of them which have been put together to what we call a tile. These tiles are distributed over some 5 kilometers or so. So as the name of the MWA emphasizes, Murchison Wide Field Array, it has a very wide field of view, which means it can look at a very large part of the sky at the same time, right? And it has a small footprint, just 5 kilometers, but it has a very large number of elements, 256. GMRT, on the other hand, is a very different class of instruments. It has only 30 elements, 30 antennas, but each of those antennas is gigantic, is 45 meters in size. The collecting area of whole of MWA with its 256 elements is about 8 GMRT dishes. GMRT is spread over 25 kilometers, so it offers much higher resolution. GMRT operates from 150 megahertz to about 1450 megahertz. MWA operates from about 80 megahertz to about 300 megahertz. So GMRT also samples a higher part of the frequency band as compared to the MWA. So depending on the nature of the object you're trying to study, if I'm looking for more sensitivity, higher resolution, then I'd go to GMRT. If for whatever reason I need, I'm doing a survey which I can get away with low sensitivity, I'll go to MWA. Besides, as you know, the frequency at which you're observing is going to decide the physics which you are going to be probing, right? So if I'm looking for, say, neutral hydrogen in nearby universe, I have to go to GMRT because there I can see, the 21 centimeter line. MWA, I cannot see it. If I'm going to very high redshifts, then MWA can still do that for me.
Yeah. So if you kind of want to target your star or say a galaxy with a high precision, then you would go to GMRT, and if you have to do a survey, you would go to MWA, right?
In some ways, yes, but it's a more nuanced answer than that as well, yeah.
So with India having this state-of-the-art facility and we have the UGMRT working now, so where do you think we stand in the whole radio astronomy scene in the global context with the SK going to get operational in coming years?
Correct, yeah. So, as astronomers, you're always looking for, more and more sensitive instruments, higher sensitivity, bigger telescopes, right, yeah. So, as things stand right now, if you were to make a plot today, which would have frequency on the x-axis and sensitivity on the y-axis, you would find that at the frequencies where GMRT operates, right now there is no other telescope which is more sensitive than GMRT for most of its frequency band. It will get surpassed by SK whenever SK comes. Right? SK is also a giant which will only slowly wake up. So, I mean, it's that's true of all interferometers because they have many elements. When they start, only some small fraction of them are commissioned, and then with time, more and more of these are commissioned. And so, right now, GMRT is, of course, leader of the pack. But even in the SK era, there's going to be only one SK, right, which is going to serve the needs of all the astronomers in the world. So the observing time on that will be very competitive.
Yes.
So for many of the ideas which you want to try, you will be first told that why don't you try things out in a pilot somewhere, and let's see what does that idea bring you. If there seems to be some merit in that idea, then
we can move it to SK.
So you will have to test the worthiness of many of these ideas before you will get time at DSK to observe them. And GMRT would be one of those instruments where you will be able to do that very well. That is one class of things. There's another class of things where you really need to sit and stare at something for a while. For things like that, it will be very hard to get time at DSK because so many people will be pulling for time at DSK. So there will be a bunch of niche projects for which GMRT would remain the best instrument for a long time to come.
So with the SK going to get operational, what is some exciting future science in solar astronomy do you think that you can do with the SK?
Sure. So, it's really surprising that how complicated the sun is to image in radio wavelengths, right? I mean, why is it so hard? It's the brightest star out there. You should just be able to go and see it. The problem is that the solar radio emission varies very quickly in time and in frequency. And if you were to make an image of that, then in the morphology of that image, if you were to look at the polarization properties also change very dramatically, very quickly. So over a fraction of a second and over less than 100 kilohertz, all of these can change. And traditionally, the radio telescopes which were designed, they were all designed to be so-called synthesis telescopes. What that means is that I'm going to gather my data across some time interval and across some frequency range and put it all together to make a single image. That approach doesn't work for the sun. Okay, I need to gather all of the data
in real time.
Right. Certainly in real time, but I want to make an image, a snapshot over a fraction of a second. So I need to gather all that information very quickly and across a very narrow band, 100 kilohertz, 200 kilohertz, something like that. So the larger is the number of elements which I have in my array, the larger is my capability to gather this information, because radio interferometry is a so-called Fourier imaging technique.
Yes.
What that means essentially is that radio astronomers think of their telescopes in terms of baselines, right? So any two telescopes, any pair of telescopes forms a baseline. Each of these baselines is measuring an independent Fourier component. And my job is to collect all of these Fourier components and do an inverse Fourier transform to make an image of the sky. So naturally, the larger is the number of Fourier components which I can capture, the higher will be the fidelity of the image which I get out of that. And so that is where instruments like SK will help us, because they have the largest number of elements. And they are also spread across quite a bit, so they will give me very high resolution, and they'll give me the best Fourier coverage I can get, and therefore will be able to deliver the best images which have been made so far.
Yeah, so that is a very exciting prospect. So as soon as we can see better images of the sun, as we already are kind of reaching reaching the ceiling in the solar scene right now. So recently we have made a horn antenna in our campus. So it's a very small campus project. So what science do you think we can do with the small horn antenna? And
so certainly you can point it to the sun.
Yes.
Yeah. So that is undoubtedly the first thing, I think, which perhaps you have already done to look at what you're getting, to measure the beam shape and so on and so forth. What is the size of the horn? Yeah.
It should be around, I think
Half
they
a meter?
modified it. Yeah, half a meter is fine, yes.
Yeah. So I think with something around that size, you should also be able to see the galactic rotation curve. So that's again a very exciting project, pointing it in different directions, getting that estimate, pulling that data together, to make a plot of the galactic rotation curve. Those would be, I think, some of the first projects which you should do with that. Yeah.
Yes, so thank you for your suggestions. Now, in your, say, very long journey in astronomy, what has been the most exciting discovery, or what has been the most exciting result that you have had in your life as an astronomer?
So I'll give you two.
Anecdote, yes.
Okay. So one was, we were talking about nanoflares earlier. So one of the reasons I got really excited about solar radiophysics during the early phases of MWA project was because people had already been looking for nanoflares, found them, but also found that they are not suitable for coronal heating. Now, the same plasma which was going to give rise to nanoflares was also going to give rise to a radio signature. Now, that radio signature was going to come from a coherent emission mechanism. Now, the nice thing about a coherent emission mechanism is that it produces a very large observational signature, right? Just like your laser pointer, it's a few milliwatts, but I can see it almost a kilometer away, right? While my candle is many more watts, but I can barely see it, from the other end of the room. So because of that, I wanted to look for signatures of much weaker analogs of these nanoflares or femtoflares or whatever in radio wavelengths. But it was very hard to do because these things are very fleeting. They last for fraction of a second over few order 100 kilohertz, and they just come and go. They'll be very weak, order 1 or 2% of the background. So we were able to convincingly detect these sometime in 2022, I think, or 21, 22. That was really exciting. So that's something which I'd been dreaming about since around 2004 when we were writing the science proposals for what is it that you want to do with this. So it took us about 20 years, but we finally saw them. And we were sort of right in supposing that, they should be there. We now have irrefutable evidence that they are indeed there. They are all over the sun. They are also there in the polar regions of the sun. The problem is that from looking at the radio signature, you cannot easily go back to the amount of heat which must be dumped in the corona to produce that. So we are not in a position to answer the coronal heating problem. But we are certainly in a position to say that these things are taking place and must be contributing to coronal heating. That's one aspect. The other thing which I wanted to mention is something which completely surprised us and which we still don't understand very well, which is the fact that we see the presence of linear polarization in active solar emission. Active solar emission means, any kind of burst. And it seems to be there in most kinds of bursts which we have seen so far. And the problem is the following. You're all familiar with Faraday rotation. Right, so when linearly polarized light is passing through magnetized plasma, it is going to Faraday rotate. Sun has so much plasma and sufficiently strong magnetic field that this should have undergone many, 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 many turns. So that no matter how small is the spectral band in which I am observing, it should have essentially depolarized because it has rotated many times. So if you want to think about it in terms of numbers, 10 to the power 5 is the expected rotation measure, which should completely obliterate any linear polarization. But we see it. We spent a long time trying to, test where am I making a mistake? Is it something instrumental, something in my analysis software, whatever. We finally ended up observing with two instruments at the same time, at the same frequency. One was MWA, the other was GMRT, both looking at the sun. And we find consistent linear polarization signatures in them. Right? These guys are 8,000 kilometers apart. They are very different in design, very different ionosphere, independent software framework, different kinds of, artifacts which are present there. So clearly it is not coming from the instrument. It has to come from
The sun.
the sun. So that was really surprising. And yeah, we're still trying to understand why it is there, but we don't doubt its existence. Yeah.
So that is indeed a very surprising thing to know. Maybe some of the budding astronomers, solar astronomers will get into it. Now, this brings me to my last question, a question that is in the mind of every undergraduate that is interested in astronomy. It is, what is a non-negotiable if you are going to go into academia as an astronomer? So what steps do you have to take if you are an undergrad, if you're interested in astronomy and you see yourself as an astronomer in the next 10 years? What do you think one should
I think
do?
the first non-negotiable is passion. You really have to want to do it. Right? I mean, it's not a road to somewhere. Right? It's not, so you're doing it because you want to do it. That I think is perhaps the most important reason. Yeah. The other thing I think is that you have to remain open to learning. So it's very hard to predict what is it that you will need to learn. Some things, yes, I mean, okay, you've chosen your area of work, that will come with certain areas of physics and maths which you need to learn. But every so often you will find yourself working on something which requires you to build a skill which you do not previously have. So your openness to learning and retaining the ability to learn, I think, are perhaps the most important things which you need. I would also dare to say that this is not specific to astronomy. I think this is sort of more
very general.
Yeah, has general applicability. But I would say is that it is a very interesting time to think of astronomy as a career, because across a whole range of wavelengths, there are new instruments which are coming up. Also, because of the vast advances which have been made in our computational capacity, a lot of problems which were earlier untractable because we could not afford the computing for them have become tractable. And with, things like machine learning, where people are trying to build different emulators to accelerate things, and even larger class of problems which are hard to do are becoming more accessible. So I think the canvas which you have to play with is very large and very interesting. Yeah.
So yeah, that would be the end of our discussion. If anyone from the audience has any questions, they can ask.
What are scientific proposals? You mentioned that while, before building a telescope, you give a scientific proposal.
Right. Yeah.
So, what is it?
Yeah. Okay. So a scientific proposal in this specific context is a justification for why should somebody give you the money to do it, right? I mean, you're building a big and expensive toy, right? It has to serve some purpose, and some benefactor is going to give you that money. These benefactors in our context are usually governments or some philanthropist, right? Yep. So they are, of course, looking for the best outcome for the resources which they are going to give you. So they need you to justify what is it that you want to do with this money and why is it that a good thing to do. And you will be competing against many other people who are also looking to get that money to build their toys here. Right? So that is the scientific justification which you need to give, that here is the instrument which we want to build, here are the capabilities, and if it has these capabilities, here are the science areas which we will be able to explore, and here are the data products which we will be able to deliver. So that is the science proposal in this case here.
Yeah.
Yeah.
So, yeah, we have another question.
So, you said magnetic connection releases a lot of energy. So, or just energy in general. When there's mass ejection coming towards Earth and there's lots of charged particles, we see auroras because they travel along the magnetic lines. But you said that the magnetic connection happens first. Can you detect the magnetic connections earlier before they reach the poles? So, and do they also produce a light, or do they?
Sure. So the aurora you would actually see almost all the time, right? So there is always a little bit of stray magnetic field, irrespective of whatever is happening. There is some magnetic field which will reconnect and particles will flow along the poles. You see more of it during maxima, less of it during solar minima and so on. But some of it is happening all the time. About your question about can we detect the magnetic reconnection earlier? What you really want to detect is the possibility of magnetic reconnection, right? What you want to detect is what is the orientation of the magnetic field in the coronal mass ejection which is coming towards me. So right now, our best way of detecting it is via the satellites which are sitting at L1 point. L1 point is just 1.5 million kilometers towards the sun, right? That's like 1% of the AU. These things are moving very fast. The faster ones, which are also the ones which inflict the most damage, they are moving at 1,000 to 2,000 kilometers a second, which means that it will take them about half an hour to come from the L1 point to the Earth. Which means that even if you were to measure it, which these satellites are perfectly able to do, you don't have sufficient advance warning to respond to that. Right? That data has barely made it to the ground, right? Because, you would download the data only when you have the visibility of the satellite. That's usually a few times in a day. Yeah. But this guy is going to reach Earth in half an hour. So you can get the data, you can use it for scientific studies. You cannot really use it for forecasting space weather because it doesn't give you enough lead time. In fact, one of the things we are working on in my group is to try to measure the orientation of this magnetic field while the CME is still quite far away, closer to the sun than it is closer to the Earth. That is again using Faraday rotation, that the CME has plasma, it has magnetic field, I have linearly polarized background sources. I can see how much Faraday rotation it is leading to. If I can see a large number of background sources through this and build a model of the CME which I can fit to all of these data, then maybe I can get a sense for what was the vector magnetic field and predict it here. That would allow you a large fraction of a day or maybe even more than a day as a lead time. That is something you can do something with. But right now it's in the future, but we are working towards showing that it is actually possible to do it here. Yeah.
Understood. Thank you.
Welcome.
So as you said, getting into astronomy and advancing into it generally requires being open to learning. When one starts, they find that most materials and most people that help you out to get introduced to astronomy generally adhere to a very terminology-heavy start, which is something I feel like is not a very major problem with most of the subjects, at least in my opinion, what I've studied. How does one cross that terminology-heavy bridge in a more efficient way? Because see, I would say that I'm open enough to learn, but the start seems too heavy, too terminology-heavy, as I said. What do you think about it?
Fair enough. So what you're saying is it's basically too jargon-heavy, yes. Right? Yeah. So there's a reason why the terminology is in place. Right. So, for example, this is a cup. I could describe it as a vessel which could hold water or any other liquid, or I could call it a mug. Yes. Right. So these just become a quick way of referring to something, right? And in a field where people understand each other, it just makes communication very efficient. But when you are trying to break into that field, it seems like a barrier because it's like when you're learning English or whatever other language, or you're reading a book with some author who likes to use really fancy words. Every sentence you are running to the dictionary to read to figure out what they are trying to say. That is the state in which you find yourself, right? That's a bridge you have crossed already in other contexts, right? You've taught yourself enough language to not require this anymore. If you stay at it, and if you were to diligently, every time you come across a piece of jargon you don't understand, at least knowledge is easily accessible now. If you put in the effort to try to understand that would make life a little easier, that it would seem like progress is slow and interrupted, and every time I'm trying to do something, there's a tangent at which I have to go. But I think that's a phase which you will eventually get over. Staying at it is the only way to do it. Yeah.
Yeah, it's the consistent effort. As you mentioned, in his case, it was an idea that was realized 20 years later. So it's a consistent effort you have to put in and you will get to it. And it's a worth it effort. So do we have any more questions? Okay, I guess not. Let me thank our speaker. Thank you, sir, for a wonderful podcast session. That will conclude the session. Thank you for joining us.
Thank you. Yeah.